Okay, so this is chapter 11. Go over this fairly quickly. Um, so this is going to be the organic synthesis part 2 of it. This is going to be some of the other remaining concepts behind it. Part of the major part of this is going to be the beginning of how do we go from a final product that we're trying to make and design the synthesis that will make that final product. So before we had talked about reading a synthetic process, synthesis, where we have different steps and we would follow those different steps, and the synthesis was like the draft that you would follow. And you'd have to fill in the concepts and fill in the exact reaction conditions, even where we had the solvent and heat and time it took. That still would require some more steps, like do you use a spin vane? Do you use a boiling stone? Do you use a round bottom flask for that heat? Do you use a sand bath for that heat? These things can actually have some differences to them, actually. And you can get slightly different yields, you can get slightly different products, you can get reactions that just from small differences in those steps can actually give you pretty significant different yields, or even give you a end up going and making side products that you then have to purify. Because remember, typically when we're talking about mechanisms and reactions, we had been talking about major products. Major products meaning that you could have side products, the minor products. Okay, so this is a natural product synthesis. Here we have Taxol. Right there's Taxol. It's a pretty large structure as in terms of syntheses. So this is actually used in cancer chemotherapy. It was first isolated actually from the bark of the Pacific yew tree, and that's why you got the Pacific yew tree right there. It is a natural product, actually. Other natural products can include things like menthol, eugenol, vanillin, of course. We have menthol and eugenol that are found in peppermint oil and clove oil, respectively. Eugenol, clove oil, menthol, peppermint oil. Menthol's typically what you would associate with that minty smell and flavor, though there's other notes to peppermint than just the menthol. This right here is some different reactions that will alter your carbon skeleton and your retrosynthesis analysis. Retrosynthesis is going to be where we take the final product. Remember, when we're trying to get something here, when we're doing a synthesis, it's very rare for you to just be taking random reactants, throwing them together, and you're trying to make a random product. Typically you're going to be going towards an end product that you already know what that looks like and what that should be. You usually have a spectra of that already. You usually have a structure more or less worked out, and you're trying to get the end product. And so retrosynthesis is taking the synthesis and writing it backwards. And so we start with the end product and we work our way to substrates that we can purchase or that we have available to us. And so we're going to work the reaction back way. Reverse synthesis, or retrosynthetic analysis, being the analysis of the reverse synthesis. Okay, and so right here, this is the starting compound class, the typical reagents and reactions and conditions, and the compound class formed. These are these tables your book provides. This is typically what would be referred to as a retrosynthetic, or they would be considered the sort of stuff you would look at when you're trying to do something like click chemistry. Click chemistry being a retrosynthesis where you just look at this part and you try to assemble a synthesis from that. They give you the sort of transformation that would happen, and then a very generalized reaction condition that would go along with it. Now your book actually takes an extra step further and gives you the key electron rich species and the key electron poor species, and comments detailing the type of reaction or elementary reaction steps that would be involved, and then gives you the portions of the book that further discuss that. Now, this same sort of thing is actually on the web, and if you're ever having to actually synthesize something and do this, I would actually recommend you do something like organicchemistrywebportal.com, I believe it is, or one of those sort of sites. There's actually sites and apps that are sold. The apps are expensive. They can range from like $10,000 per terminal, and I've even seen ones that are more, but I think that's gratuitous probably. The 10,000 one was really good actually. But and there's cheaper ones, a little bit cheaper. You can get it down to somewhere in like the $4,000 or $5,000 per terminal sometimes. But anyways, what they do is they take this information and put it in databases, so you can actually, and if you go onto the web, you can do different types of transformations, i.e. going from adding an extra carbon to something, adding a triple bond to something, taking a double bond, going to a triple bond. You look up those transformations, and then it tells you the reactions that would do that. So it then give you all the reactions that would add a triple bond to something. And then you can go further into detail, and it would give you sort of conditions under which these things work. And then it would give you mechanisms and different papers detailing different conditions, and it'd have all those things linked into it. And so then you can very quickly work up a synthesis. Now the apps are amazing. You can basically do a reverse mechanism. So you can take a retrosynthesis, add in the steps that you want it to go through, and it will actually then link all the reactions that would possibly do that. And then you can go through the reactions and look and wonder which ones will give you the correct conditions that you want to do this reaction under, and which ones won't target other functional groups that might be there. And it actually, depending on the app and how advanced it is, will flag things. Like this would react with an alcohol, and this will also react with an ether. And so you have an ether and alcohol, and it'll flag it, hey, this would react with both functional groups. So these apps can get really good, actually, very helpful. But however, you would actually need to know nothing's perfect, everything has error in it, and so you do need to understand to some degree what you're looking at to be able to actually work with this. Okay, so this right here is going to be the alkylation of a terminal alkyne. And so what we're going to do is we're going to add a CH3 over here, and that's going to make a new CC carbon bond off of a triple bond. Now, this is very convenient because these triple bonds are fairly reactive species. They're they're reactive in a way that is not reactive, say, for a double bond over here or a triple bond that was in the middle of a chain. And they can then be you can add lots of other stuff to those areas, or you can just hydrogenate them and make the triple bond go to a single bond with hydrogens across it. So you can have lots and lots of options. This is a very nice reaction, very nice tool to have in your toolkit. And so the first step of this is going to be adding a strong base to this. It needs to be a very strong base because this is not that acidic. And so we use a hydride in this case. And then the next step of the workup is going to be after the proton transfer, and you generate that negative charge on that triple bond there. That's then going to be an SN2 reaction where it's going to target the CH3, and the iodide will be the leaving group. And that would give you your methylation. Notice that this could be a methyl, of course, which is what we're doing right here. But we could add any alkylation. This could be a very long chain, right? This does not have to be CH3. It could be C20, okay? You just need to be able to get the solvent correct so you can actually have these things come in the same phase. All right, so this one's going to be a conversion of an alkyl halide to a nitrile. So we have our alkyl halide here, bromide in this case, and we put this with this very, the sodium nitrile, or the sodium cyanide. And what this is going to do is this is going to give us this negatively charged carbon right here. That's then going to attack in a SN2 reaction. You will need DMSO typically for this. There's a few different solvents that will work, but DMSO is going to be a very good one for this. It's a polar solvent that's aprotic. This is going to then attack this carbon. The bromide is going to leave as your leaving group, and this is going to give you your nitrile functional group then. So there's excellent yield, 86%. Anything over 70% is pretty good yield. 86% is excellent yield. If you get into the 90%, that's really impressive. And you could probably manage to get this up into the 90% by tweaking these reaction conditions and time. But that takes a lot of effort, and that's something that you'd have to do if you want to get a synthesis that is a very long synthesis. One of the things I want to point out at this point that we're starting to talk about, like the amount of product you're going to make here, your yields, is that if you have an 86% yield, that seems really, really good for one-step reactions. But if you do that 20 times in a row, you've lost almost all your, you're going to make very little product for a lot of reactants you have to put in. And so when you start doing these very long synthesis, you need to start pushing these things up into the 90-something% yields. And this actually becomes big, 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 big money. Okay? When you're talking about like a pharmaceutical factory, changing one step so it's no longer an 80% yield and rather you get a 90% yield could be the difference between tens of millions of dollars a year. It could be a massive difference. Some of these reactants you're throwing in here are quite expensive. So getting a way to recover these or getting a way to increase yields is actually big business. Incredibly important, a lot more important than people realize. So the structural features that surround new carbon-carbon bonds in the product are going to provide clues to which reaction can be used to make that bond. The reactants, when we're doing this in a retrosynthetic, we typically call these precursors. They're the things before what we want. That would be necessary to carry out that reaction are going to need to be carefully inspected for identities and locations of their functional groups. Because keep in mind that like having the alkyne at the end here, a terminal alkyne, is actually incredibly important to this reaction, right? If we don't have a terminal alkyne in this reaction, it is not going to go. And so here we have a terminal alkyne. It's being combined with the other side of that alkyne, which will be this R prime here. And these are the precursors that can work. This actually does create this product. On the other hand, if we were to try to do this with a different precursor where we had a carbon over here, this would no longer function in this reaction. And so notice that this is the normal area you've always seen. You may have actually seen this hollow arrow in different places. It does show up on different chemistry tools. People put it in there. It's actually kind of funny because a lot of chemistry tools that have it never get used to make any retrosynthetic anything. And so it's kind of an amusing thing. But this hollow arrow here, this is actually means retrosynthesis, that we're doing this in reverse. So this is our product here, and these are our precursors. So what you'll notice is that we've written our product right there that we actually want to make. We put retrosynthetic arrow, and then these are going to be our precursors that we'll use to make that. And so this is referred to as the transform. This is the proposed undoing of a single reaction or set of reactions. You can actually write a transform for a series of reactions. In this case, this is actually a series. Right here, there's two steps to this reaction that we're looking at. And so again, that's the open arrow. It's the retrosynthetic arrow. It's the convention that's going to indicate a transform. So this step right here is a transform. And we draw it from the target that we want to the precursors. Notice the language completely changed, so people don't get confused and make mistakes. So right here we see a target, and then we do a transform. We put a retrosynthetic arrow again, and then these right here are going to be our precursors that can make that product. And so if we were to look at the reaction, it would be these two things coming together. Those would be our reactants, and this one would be our products. So whenever we do this, we'd write out our retrosynthesis, and then we would go back and we'd make sure everything works, and then we can then flip all the arrows, write it in reverse, and that's going to be our synthetic pathway that we can then work to further develop and make the special drug that's going to cure the thing that we want to cure, or be a pretty color. there's an incredible variety of things. A new taste. Chemists do like everything in the world. There's a chemist everywhere. So this is going to be, we want to undo this alkylation. We know that we somehow need to get here this structure. We don't have this structure easily available, or we're trying to make this cheaper. And so we're going to undo an alkylation. There's a few different ways we could theoretically undo that, but we're going to do it on one of these two sides. And so we can do it on this side, or we could do it on this side. This would be that methylation again. This would be the other alkylation that you could have done, in which case you would have taken the triple bond on this side, which is your propine. This one here has the chloride on it, and so that's your alkyl group. Okay, so this right here is going to be, again, the retrosynthetic transform. This one over here, then, it would be your synthesis pathway. So in the synthesis pathway, again, we use the normal arrow for reaction. This is a reactant. This is going to be our product. So these are our reactants right here. These are going to be our product. And again, this is the different steps, because in the synthesis, you have to flesh this out a bit, because you're actually going to be doing the synthesis now. This is how you would do it temporally, right? This, you have to start with this, put this together, and then the next step is you put this in. A retrosynthesis is completely reversed. We actually start at the ending, because we're trying to draw the pathway to it. It's kind of like if you were to take a map and you're trying to figure out, how do I get to Chicago? You don't start at your starting point. You would want to take your ending point and work backwards towards where you want to actually start from. That's how everything works if you actually want to plan things out. You always go where you want to end at, and you work backwards to where you currently are. So this is again going to be another approaching a synthesis with a functional group transformation. In this case, we're taking the primary alkyl halide and we're transforming it to an ether. This would be the synthesis, and this would be the two reactants we have to do together. Notice that this right here would then be your transform, and this is going to be where we show we want to break that product, and so we want to add these two together, and this is the bond we're going to create in this. We can mark this as we undoing a Williamson ether synthesis. We want to give us some more details here on the sort of mechanism we're looking for, or what we're trying to aim towards. And then these would be the reactants that we would have to put together to give these, or specifically in this case, they'd be called precursors, and that one would be called our target, if we're talking about this as a retrosynthesis. So here's the steps you need to take in a retrosynthetic analysis to create a retrosynthesis. Number one is going to be examining the target for a feature that could be made from a known reaction, something you know that works. Number two is going to be applying a transform that would undo that reaction you have in mind in order to determine the precursors for that reaction. Number three is going to be examine which precursor for a feature that can be made for a known reaction, i.e., can we make that triple bond? Can we put together the two hydrocarbons to create that specific structure? Again, these are going to be multiple step typically until you get to stuff that you can actually buy for reasonable prices. Number four, for each precursor, you're going to apply a transform that undoes the reaction you have in mind. Number five, you're going to continue applying transformers until you arrive at starting materials. Starting materials can be somewhat of a nebulous concept. Starting materials are things that you can obtain for a reasonable cost, something that you are willing to give up for them. For example, I can purchase almost any starting material, but some starting materials could cost $10,000 for a single gram of them. And so that's no longer actually some starting materials can cost. I've seen a starting material that somebody tried to do at one of the labs, and they tried to order it, and it was $10,000 for a milligram. Uh, and basically, they were going to order it from this manufacturer who would have done a targeted synthesis to make this thing on one-off transformations. It was just absolutely ridiculous. Uh,